Computer. So what we're going to do today is we're going to continue the lecture and the discussion on groundwater and soil. So that is what I hope to achieve today, get you guys to understand groundwater and its relationship with soil, right? It is within soil. So when you look at groundwater at a surface level, so we're standing at the surface. I should have used a different color. Surface, buildings, trees, and so forth. So in general, let's say we're performing a site investigation, right? We need to drill. And then we're going to put a well in place. When we look at a soil sampling event or a drilling event, generally we'll find topsoil. So usually we'll find topsoil. And then in many cases, we might find a layer of fill. The topsoil might be only a few inches thick, but in many cases, we will find a layer of fill. And what is that? That is soil or material that has been placed by humans in construction. And then you get into the native material. And that the native material could be sand, silty sand, clay, or so on. Let's say you've got a layer of silty sand. Then beneath that, let's say you have a layer of sandy gravel. That's why you've got the aquifer there. At some point, you're going to run into what is known as the water table. That is the groundwater that exists. That's the groundwater that exists in the subsurface. And where does it exist? Well, if you've got soil particles, there's pores between the soil particles. So it exists. Groundwater basically exists. I'll write this in red. Groundwater exists in this pore spaces between the soil particles. And this, now the soil that's above the water table is known as the vadose zone. Vadose zone. Whereas the soil beneath that is going to be known as the saturated zone. And when you install a well, let's consider that we've installed the well. Again, let's draw the land surface. And we say we've installed a well. What we're trying to do is intersect the water table. So we drill a hole, we put a pipe in place. What we're trying to do is intersect the water table. Why? So that inverse triangle is the water table. Why? Because we want to measure the water level. We want to Why do we want to measure the water level? Well, there's a few reasons for that. One could be you're at a construction site. Your project is a construction project. you want to know if you will have to dewater. So for construction reasons. Second, you might be performing a environmental site assessment. Or you might be performing a water study, water resource study. You want to measure the water table. Right now, you are studying surveying, right? So in surveying, let's say you're set up, you're taking you're set up with your rod, you're taking a reading, right? And you're going to use that information to determine what the elevation is based on your benchmark. I'm assuming you're familiar with these terms now. So now you have an elevation of the ground surface elevation. And compared to that, you're measuring the depth to water. Now, based on that, you can now determine the elevation of the groundwater. So let's imagine that we do that at our site. Let's imagine that we do that at our site. Let's first draw our site. Bird's eye view of our site. So this is our site, an irregular shape. So we've got, so this is monitoring well 1. Monitoring well 2. And monitoring well 3. And let's say the elevation here is 160. Oh, this doesn't work. 166.50. That's the elevation. I'm going to write the elevation of the ground surface. Meters above sea level. So the elevation here is 162.11 meters above sea level. And let's say the elevation here is 171.1 meters above sea level. But when you measure the water from the ground surface, you got the depth of water here. Let's say it was 2.1 meters below grade. I should do it differently. 2.1 meters below grade BG. Let's say here it is 4.1 meters below grade. And let's say here it is 1.1 meter below grade. You can use this information to determine the groundwater elevations. So we make a table here. First, we do the location, elevation at the surface, depth to water, and groundwater elevation. So you'll see why measuring groundwater is so important. Monitoring well 1, monitoring well 2, monitoring well 3. So monitoring well 1, the elevation is 166.50. Monitoring well 2, it's 162.11. Monitoring well 3, it's 171.10. Depth to water for monitoring well 1 is 2.10. For 2, it's 4.1. For 3, it's 1.1. So let me get out my calculator. What you do now is you deduct this. It's 166.5 minus 2.1. It's 164.4. 164.4. What I'm going to do is now I'm going to erase all of this and just have one number. 164.40 meters above sea level. It'll make more sense once I've erased everything. 162.11, 162.11 minus 4.1 is equal to 158.01. And the last one is 171.1 minus 1.1 equals 170.00. So, okay, that was correct, 164.4. That's good. Let's go ahead and draw this. It's 164.4. Animal 3 is 170.00. Monitoring 2 is 158.01. Now what we can do is we can contour this. The way I'm going to contour is I'm going to draw a contour for 160. 160.00. The next contour is 162. 162.00. Third contour is 164. 00. Next contour is 166. And then 168. So these contours can now tell us which way the groundwater is flowing. What you do is you draw arrows perpendicular to the contours. In general, you can say the groundwater is flowing this way. And if this is north, you will say the groundwater is flowing south west. You can also determine, using this information, you can also determine the hydraulic gradient and the velocity if you have further information. This is why it becomes very important to understand what the elevation is and what your water level measurement is. So let's watch somebody take that measurement. Now, this is not a real wells. So I'm going to show you how it would look like in a well.
I have.
Now, if it's lower to that level, you can actually determine what the water level is. Okay, let's go through a clip of somebody discussing what is groundwater.
Most people get their water from one of two places. City water is usually taken from surface water resources, treated, and piped to your tap. But if you live in an unincorporated area, you might be getting your water from a smaller on-site well. This water is from underground aquifers, also called groundwater. So, what is groundwater? It's water that collects or flows beneath the Earth's surface, filling the porous spaces in soil, sediment, and rocks. When we say something is porous, that means it has small spaces or holes in it, through which liquid can move. Porosity is an indication of how much water a material can hold. When we say something is permeable, that means it allows liquids to pass through it. Permeability is an indication of how easily water can move through a material. Materials like gravel and sand are permeable and porous. Water flows through them easily, and they can hold a lot of it. Materials like clay and shale are porous and can hold water, but their pores are so small that water flows through them very slowly, giving them low permeability. With this in mind, let's talk about aquifers. An aquifer is a saturated area of sediment or rock that groundwater can move through. Groundwater stored in aquifers can be brought to the surface using wells.
So you can imagine if you think about something like the Grand Canyon and you can see all those different layers, well, some of those layers hold water better than other layers. And so they're all sandwiched together and interconnected in various different ways. And because it's all underground, it's hard to know about how exactly they're interconnected, but they're stacked on top of each other. So when you drill a hole in the ground, you drill through some geologic formations that aren't holding any water, and then you can drill down into one that is.
We use wells, groundwater wells, for all kinds of purposes. So the typical shallow wells here in this vicinity would be down at about maybe 200 feet deep from the ground surface, but they're pumping water from 60 or 70 feet, and they're pumping it from a water table or unconfined aquifer largely.
So a confined aquifer, if you go back to imagining the stacks of different rock types, if you think of it like a sandwich, like if it's a BLT and it's a slanted BLT, then if the tomatoes are the water holding geographic feature, then the water flows down through the tomatoes. But if the bread is impermeable to water, the bread is then confining the aquifer in the tomatoes. And so because it's on a slope, water keeps pushing in, and so there's pressure on the water from the top of the hill to the bottom of the hill. And then the cool thing about a confined aquifer is if you drill down through the bread into the tomatoes, you can get water to come up under pressure. And an unconfined aquifer is just one where it has contact with the surface, and so there's nothing holding it in place.
Water that collects underground is held in an upper unsaturated zone and a lower saturated zone. The unsaturated zone is located directly beneath the land surface, and the pore spaces hold both air and water. In the saturated zone, all the open spaces are filled with water. The water table is the very top of the saturated zone and the bottom of the unsaturated zone.
Well, the saturated zone would be all of that soil or whatever the lithology is at depth that's below that surface water level, or we call it the free water surface, that you would intersect when you drilled the hole, say, and you dropped a float in, and you'd see this water standing, or like standing water. So it's all of the soils or lithology below that free water surface is considered saturated. There's a zone above that called the capillary fringe, or has some other names, or seepage face, that's also saturated but held there by capillarity. So like a capillary tube sucks water, like a straw, a thin straw, out of a beaker. The capillary fringe holds water in the saturated, it saturates the soil there, or nearly saturates it. Above it, the soil begins to desaturate, associated with the capillary pressures in the water, in the soil water, until when you come near the surface, it's relatively dry if we're away from, wet areas.
Water table.
That does not apply to situations where you're near a wetland. If you're near a wetland, then you are going to see the groundwater and at the surface.
Is just sort of the common word that people use to refer to aquifers, but it's a little bit confusing because it sort of implies that there's some sort of table underneath there and it's just this giant lake underground. And because of the way rock formations are formed and interlayered, it's not really the way things are. And so while basically when people say water table, they're talking about the depth that you have to drill down to hit water.
What does it mean to recharge the water table?
You can think recharge the groundwater table is basically put water into that aquifer. It's like imagine if you had a glass full of sand and you could pour water into that glass even though it's full of sand because there's all the little holes in between the sand bits. And so you could pour water in there, and then if you drill the hole in the bottom, water would just leak out the bottom. And so the more you pour water in the top, the more you're recharging the ground table or filling up that aquifer.
I'm interested in that recharge area, or that zone that we sometimes refer to as the vadose zone. So vadose just meaning the unsaturated or partially saturated zone. And looking at agricultural recharge in particular, for example, irrigation of orchards or regular row crops or alfalfa hay crops, and seeing what fraction of that, leaches the root zone or moves through the root zone and, is beyond the crop demand and goes down to the deeper groundwater.
How do surface water and groundwater interact? Some rivers and streams gain flow from groundwater, and others lose flow to groundwater.
This is important. And this is something I want to touch on in a lot more detail now. If you're looking at groundwater, again, let's draw land surface. So let's say this is a stream or a lake, not really lake, but creek. Groundwater tends to be connected to it. And so what generally happens is groundwater flows to the nearest water body. Most of the water that you see in a perennial or a river is groundwater flowing through the subsurface. This is in normal conditions. Normal. In drought conditions, it becomes the opposite. Sometimes what happens is then the water from the river would start to, so let's say we'll do the reverse, we'll use purple or red for the reverse. In drought conditions, the groundwater is being recharged by river. And that's why you start to see dry riverbeds in droughts, or the lowering of the water levels in lakes. But there's a connectivity. There's a connectivity between groundwater and the surface water. And so that's what I was saying, by surface water, I mean wetlands, lakes, streams, creeks, rivers, all the way to oceans. Yeah, you can also see it. It flows to the ocean as well. Now, that's an interesting scenario that we don't deal with here. But in that case, what we have is salt water intrusion, depending on how far you are from the ocean. Because that can also cause issues as well. Yeah, oasis as well, for sure. We don't have a desert nearby, otherwise that's definitely a good case study.
The streams flow across the surface, over some permeable layers and some impermeable layers. And so and also the streams themselves carry a lot of gravel and sand. And so they lay down a bed of permeable sediments. And so water can flow down through that gravel and sand into the groundwater if it's an unconfined aquifer. But if it's a confined aquifer and there's a clay layer like that piece of bread on the sandwich that the water can't get through, then it doesn't flow down into the groundwater. And then also you can have losing and gaining reaches. And so some reaches of a stream are leaking water into the groundwater, and the groundwater is pushing up into the stream.
How does this all relate to our own Santa Rosa Plain and Laguna wetlands?
Wetlands are kind of complicated because you would think it's a giant puddle of water on the surface. Wouldn't that be a great way to recharge the groundwater table? But the fact that it's a giant puddle on the surface suggests that there's no connection to the groundwater, because if it was connected to the groundwater, it would all drain and then it wouldn't be a wetland. And so wetlands themselves are not great groundwater recharge features, but they do create sort of a dam and back water up above them. So water flows across the Santa Rosa Plain and then hits this feature, the laguna, and that does trap water that people can then use as groundwater.
Whether your water comes from city pipes or from a well, groundwater is a resource we all share. It is our responsibility to manage groundwater sustainably so that future generations will have access to safe.
Okay, so let me show you a different clip that is really good.
Most people get their water from one of two places.
All right, today we're going to be talking about groundwater, and
Maybe we'll look into it in a few minutes. Let's go back to our lecture slides. So we're talking about how you can take water levels. Interestingly, you can have wells next to each other, but at the bottom of the wells, you have a screen where you allow for the water to flow into your well. And you have a water level tape that helps you measure the water. And you might, in order to run calculations, you want to know the distance between two locations and also um, the difference in elevation of the water in order to determine the flow. And so in this case, you would say the water level, or the head H1, is higher than the head H2. This might just be a function of the well being drilled to a deeper depth. Here, you've got an unconfined aquifer, and you've got the elevation heads shown here. And in each well, the water is at the same. Why? Because it's the same formation. It's at the same depth. But if you're flowing through media and you've got different elevations, you will see water flow through like it's flowing through an aquifer. And that's usually what happens, because I want you guys to remember something. In reality, when you're talking about an aquifer, this is how we define it. This is how I would define it. It's a geological formation that allows for the storage and flow of groundwater and has I would say that as well as flow, as well as, and has a recharge slash discharge area. Has recharge slash discharge areas. So what does that mean? That groundwater or water would enter in one location. So let's say that's the ground surface, right? Water enters the aquifer here. Let's just draw the aquifer. I'll draw it in green to make it easy. It's the aquifer. Ground surface. And the aquifer basically discharges into a stream. Water enters here, it flows through the geological formation. This is the recharge area. It might be in a mountain or in a zone of higher elevation. And this is the discharge area. And what makes the geological formation permeable? Sometimes it's porosity. So that's the pore space between soil particles. And this determines the permeability. And back to the slide. So let's say we create a fictitious aquifer using sand in these pipes. We've got the direction of flow of water. Why? Because the water is at a slightly higher elevation over here. As opposed to over here. And this would be the discharge area. So water enters the aquifer through here and it exits the aquifer here. So you'll have a difference of hydraulic head H1 and H2. And you can also calculate the flow area. The difference in this elevation divided by the distance is known as the hydraulic gradient. Darcy was the one who really worked on this in earnest. And he created the equation Darcy's law. So we'll get back to that in a few minutes. I do need to make sure that you guys understand what groundwater actually is in order for that to make sense.
And the different types of water tables or aquifers that we see under the Earth's surface. So groundwater just refers to any water that we have stored within the open spaces or pores of our bedrock. So it might be a little bit surprising to think about rocks because we think of them as these solid things, but we actually find out that there is a lot of open space inside them, and that open space stores air and it stores water down below the Earth's surface. So when we go and we look at this, groundwater is very important. It is a big source of fresh water. It stores about 14% of all of the Earth's fresh water. Okay, and then again, this is just any water that's stored within those pore spaces. Okay, so when we start talking about groundwater, there are two terms that we need to know, and those terms are porosity and permeability. So porosity is just all of the open spaces in our rocks. So these are any open spaces. And when we talk about a specific definition, this is the volume of the open spaces within a rock. So these include any pore spaces, any fractures, joints, or different like dissolution pockets, and we'll just call those different voids or cavities within the rock. Permeability tells us how easily water flows between the pore spaces. So this is really the interconnectedness.
Interestingly, she brings up a great point. One is having void space, and then one having or porosity, and then one having effective porosity. If the void spaces are not interconnected, we would not call it effective porosity, because that's meaningless. You need the void spaces to be interconnected.
Of the pore spaces. So it tells us how easily water can flow. So I'm just writing water flow potential. So when we start to look at different things, again, when we talk about porosity, I usually think about like a sandstone that has large grains coming together. So the pores are all of these open spots, and again, they can be filled with water. The water will stick around the grains.
So take a look at where groundwater exists. It exists around the grains. It exists. Basically, this is important, what she is showing here. Okay. Also, understanding what permeability is, what porosity is extremely important. Now, this is good information, but not really pertinent. It sounds good that, oh, wow, you know a lot about where, you know a lot, but it's not that important. Essentially, this is where the water exists. Pore spaces, which is what she's showing now.
And then it can also have air. So water, air, and then the actual grains. Now, depending on the size of the grains and their shapes, these pores will be bigger or smaller, and then they'll be more connected. So if the water can easily move through, that tells us about the permeability. Okay, so when we go and we try to understand things, a couple things to remember. If we have high permeability, then it flows easily. And if it's low, then we get, no or low flow. I'll just write no flow for now. All right, so this is really important when we start to look at our water. If we have a material that has high porosity and high permeability, then it will be able to store a lot of water and it would make a good aquifer. If we have something that maybe it has some porosity, it has pore spaces, but a low permeability, maybe the grains are multiple sizes or they're locked together really closely, then we'll have a low permeability, and that means the water won't be able to flow through it very well. So if we have If we have a material that slows the amount of water that moves, so water can be stored within it, but it doesn't flow very well, we call that an aquitard. Or if the layer has no pore spaces, and so the water can't get in it, and it's
So aquitard and aquaclude are important terms. So what she's describing is an aquaclude.
certainly won't be flowing through it, then we call it an aquiclude. It excludes the water, so it's an aquiclude. So those are three words: aquifers, aquitards, and aqualudes to know about. And I can put them up really quickly so that we have that. Again, an aquifer, an aquitard, and an aqualude. Okay, so an aquifer stores water, and it's going to have a high porosity and permeability. An aquitar slows or restricts water flow. Often it will have porosity, so it might have decent porosity. So we'll write some porosity and then low permeability.
Okay, I think we get that covered what we wanted it to, okay? But those are terms that we will definitely be using later on. So that covers that. Okay, it's about 5:13, so let's keep going. We're making good progress here. The Darcy's law says that you can actually, the flow is equal to the hydraulic conductivity times the area times the hydraulic gradient, dH by dL. Or if you want, you can just calculate the velocity, where V is equal to minus K in the saturated zone times dH by dL or dH by dx. So let me try to explain that a little bit better. Here's your ground surface. And you've got your two wells. So this is well one. Let's say the water level here is going to be H1 and H2. And we know that the distance between the two, let's say it's 250 meters. You've done your survey, you know what the surface elevation is, so we'll write that in red. Say it's 210 meters above sea level, and here it's 202 meters above sea level. So ASL stands for above sea level. Now, let's say you measured the water. So let's say the water was measured inside of the well. Inside of both wells. And in this case, let's say the water was at 3.6 meters below grade, BG. BG means below grade or below ground surface. Let's say in this case, the depth to water is 2.9 meters below grade. So what does that mean? The groundwater elevation here is equal to 210 minus 3.6 is equal to 202 minus 2.9 equal to, so 210 minus 3.6, that will be 206.4 meters above sea level. 202, so that will be 199, hold on, 0.10 meters above sea level. That's what this elevation is right here. 206.4, 199.1. When you're looking at Darcy's law, you can determine the hydraulic gradient equals to dH by dL. What does dL mean? The distance between these two locations. dH, the difference in the height of the elevation. So that would be equal to H1 minus H2 over 250, which is equal to 206.4 minus 199.10 over 250. Here's your hydraulic gradient. So it'll be 206.4 minus 199.1 divided by 250. It is 0.0292 meters per meters. Now, in order to determine the velocity, according to Darcy's law, in order to determine the velocity according to Darcy's law, you multiply this by K. What is K? K is equal to the hydraulic conductivity, which is a parameter that tells us how fast water can flow in that aquifer. It's a concept we're going to definitely dive into in a lot more detail. The next thing I also want to mention is that if you think about an aquifer like a block, and water is flowing through it, this block, you will have a cross-sectional area. So water is flowing through it. If you take the velocity is equal to minus K dH by dL, right? To get the flow, that's the total amount of liquid groundwater flowing through that cross-sectional area. You multiply the velocity by the cross-sectional area, which is then makes it KADH by dL. That is the part of the Darcy's law. And it's important for you to understand it. It's a part of this course, and it's going to help you later on in the semester. Okay. Any questions so far? Are you guys understanding all of these concepts? I know it's only 3 of you. I would caution you and say the actual when you actually get down to the work, unless you're working in a engineering company that does a lot of complex hydrogeological studies, the work is actually not too bad. The work is it's not too bad. These type of calculations are actually quite straightforward once you've gone through them a few times for an environmental professional. Now, if you're doing a very complicated groundwater study for hydrogeological purposes, that's separate, that's different. Okay, no questions, I guess. Hopefully, those of you who are watching the recording later on, if you have questions, please do reach out. Okay, continuing on. So the reason why we have the negative sign is water flows downhill in the direction of decreasing head. Okay, that covers that. So the porosity helps determine the hydraulic conductivity. You can see the comparable, but I want you to remember one thing. The porosity in clay is not effective porosity. Clay has a very low hydraulic conductivity in terms of meters per day. I think we need to delve into that a little bit better here.
What is hydraulic conductivity? Have you ever wondered how water moves through the ground? Today, we are going to talk about hydraulic conductivity, a key concept in understanding groundwater flow in the water cycle. Hydraulic conductivity is all about how easily water can travel through materials like silt and rock. It is defined as the ratio of the volume of water flowing through a material to the hydraulic gradient, which is the change in water pressure over a certain distance. This property is essential for grasping how groundwater flows and its role in the water cycle. In the context of Earth science, hydraulic conductivity is vital in biogeochemical cycles, especially regarding groundwater flow. It helps us understand how quickly water can recharge aquifers. Aquifers are underground layers of permeable rock that store large amounts of water. This process is crucial for maintaining water balance in ecosystems, which supports both plant life and human consumption. Several factors influence hydraulic conductivity. These include the intrinsic permeability of the material, the degree of saturation, and the density and viscosity of the fluid, which is usually water. When conditions are saturated, hydraulic conductivity remains fair.
The quick comment, sometimes it's not water. In that case, it's usually oil that they're looking at.
Fairly constant. However, in unsaturated conditions, it can change significantly with variations in water potential. Hydraulic conductivity has practical applications, too. It is used in designing irrigation systems, predicting groundwater flow patterns, and assessing contamination risks in aquifers. Understanding hydraulic conductivity is important for managing water resources effectively. This ensures that water is available for both human use and natural ecosystems. In earth science education, studying hydraulic conductivity helps students appreciate the dynamics of groundwater flow within the water cycle. It highlights the importance of groundwater in sustaining ecosystems and the need for responsible management of this vital resource. By grasping how hydraulic conductivity works, we can better understand the balance of ecosystems and the role of water in our environment. So next time you think about water moving underground, remember hydraulic conductivity and its impact on our world.
So that was a nice little clip that AI generated on hydraulic conductivity. Okay, so you can see here that the higher porosity in general, the higher the hydraulic conductivity. Not always the case, though. With clay, that's not the case. Why? Because it's the effective interconnected porosity. It does not lend to it being that good in terms of water flow. And it's usually in meters per second, meters per day, so on. Yeah. All right. And sometimes, interestingly, the best aquifers sometimes are not really soil related. They're fractured bedrock. And they can allow for the flow of water at a high rate. Usually, though, when you guys are working at a site assessment site, you're dealing with water in clay, silts, sand, and so on. So if you look at this figure, it shows how water can flow through the particles of an aquifer. Now, if it's not interconnected, you're not going to have flow. But if you have interconnectivity, that's when you're going to have flow. Now, I'm looking at this over here. Another thing I wanted to point out is that like the water doesn't flow straight. It goes through in a zigzag fashion between the particles. But then what you do is you are actually seeing the water flowing in this direction. It's the general groundwater flow path, which I've now there's a phrase that we use to describe groundwater flow. And overall, it's called groundwater flux. Another interesting thing to look at is look at what's going on over here. Effective porosity is what we're looking for. And the average velocity is what we want to understand. Okay, so let's see. We've got this question over here. Water flows through a sandy body that has been placed between two screens of the apparatus, shown below. The water levels to the left. Okay, all right. So interesting. It just shows it just shows the different calculations that they've done. Nothing to worry about right now. And this is what I was trying to show you guys earlier, how groundwater has a recharge area and then a discharge area, which is usually a surface water body. As you can see here, during regular conditions, usually streams are gaining streams where they're gaining water through groundwater. And in general, the water is connected to the aquifer, right? Here, it's interesting how the water is actually just flowing through. So it enters here and there's water flowing through. And it's probably because there's a steep or a lot of the hydraulic gradient is steep in that direction. Here, this is what happens during, let me draw this. So this is what happens during drought conditions. And on the left is what you see. Maybe I'll draw that with blue. On the left is what you'll see during regular conditions. Whereas on the right, that's what you see during drought conditions. Okay. So that's where we are with the slides. Any questions about that? No questions? Okay, I had a question, but I don't know if I can find the answer. I wanted to show you. I wanted to show you how hot Venus was.
Connect team is the glue that holds our business together.
Then I'll get to my discussion.
I feel like I've got your fingertip on the pulse.
Everyone's seen Venus in the sky, but almost no one has actually seen Venus. For years, the surface was a complete mystery, hidden behind clouds so thick not even light could get through. No photos, no color, just guesses. Until now. What you're about to see are the real images of Venus. Photos taken from the ground, scans from orbit, and shots captured by spacecraft not even designed to look at it. They said it couldn't be done. And to be fair, they were mostly right. In the 1970s and 80s, Venus was the ultimate proving ground for any spacecraft that claimed it could survive anywhere. Because this wasn't Mars, where rovers can casually explore for years. Venus was the real deal, a hellscape so brutal that sending a machine there felt more like throwing it into a furnace and hoping to hear a scream before the line went dead. But the Soviets tried it anyway. Between 1961 and 1984, the Soviet Union launched more than a dozen probes toward Venus. Most failed. A few burned up in the atmosphere. Some missed the planet entirely. But in 1975, something incredible happened. Venera 9 touched down. It didn't just survive for a few seconds, it lasted approximately 50 minutes before succumbing to Venus's extreme heat and pressure. And in that window, it sent back what no one had ever seen before. The first image from the surface of
You don't really see soil like you do here on the planet Earth.
Any planet other than Earth. It wasn't pretty. The photo was black and white, grainy. The frame was warped, and the camera, tilted slightly, pointed toward a mess of flat rocks that looked more like a construction site than an alien world. But the gravity of it, no pun intended, was undeniable. This was not a CGI render. It wasn't a radar scan or an artist's guess. These were real stones on a real alien world, beamed back from 38 million kilometers away. Days later, Venera 10 did it again, landing just 2,200 kilometers from Venera 9. It lasted 65 minutes, long enough to transmit another eerie photo filled with cracked slabs of rock under a haze. And then came the Venera 13 and 14 missions in 1982. That's when things really got weird. Venera 13 didn't just take photos, it brought color. It captured sound. It even drilled into the surface and analyzed the soil. And when its image came back, it shocked the world. The sky looked like something out of a nightmare. A deep sulfur yellow tone, probably tinted by sulfur dioxide and volcanic gases. The ground was covered in flat, interlocking rocks that looked like the crust of an overbaked pie. These weren't artist impressions. They were real, raw, distorted by heat, yes, but unfiltered. Exactly as seen by a robotic eye that was dying while it sent them. And what those early Venera missions proved was simple. Venus is not some smooth marble covered in clouds. It's broken, violent, and uninviting. Yet somehow, in those short time periods of survival, humanity got a glimpse of a place that had rejected every other visitor. And that was just the beginning. You can't just point a camera at Venus and hope for a clear picture. That's not how it works. The planet is wrapped in clouds so thick, so toxic, and so reflective that visible light doesn't stand a chance. It's not fog. It's more like trying to see through a blanket soaked in acid. The atmosphere is made of carbon dioxide, pressurized to over 90 times Earth's level, and laced with sulfuric acid droplets. From space, Venus looks like a smooth, yellowish orb, completely blank, totally featureless. For decades, that's all anyone could see. So scientists change tactics. If you can't look through something, you bounce something off it. Enter radar mapping. In 1989, NASA launched the Magellan spacecraft, a mission that didn't care about pretty photos. Instead, it was equipped with a powerful synthetic aperture radar system, SAR for short, that would orbit Venus and send radio waves straight through the clouds. Those waves would hit the surface, reflect back, and be reconstructed into high resolution.
Why I wanted you guys to watch this is to see how one of the biggest differences between our planets is a high amount of soil that we have here. And why do we have so much soil? Why do we have so much soil? And why not Venus? Because of weathering. Well, that's part of it. But initially, weathering and erosion. That's the biggest thing.
Seven days of savings at PetSmart from September 5th.
Whereas on a planet like Venus, that did not occur. Our civilization, everything that we know, everything that we are, if it isn't for soil, we're nothing.
The creation of soil has taken millions of years, but for us to truly understand it, we must first look to its origins and find out exactly how it was formed.
In essence, soil is just broken down rock material. Weathering erosion is key, which we do not have on a planet like Venus.
Fundamentally, soil is derived from bedrock, and it's the weathering and eroding of this bedrock that starts the process of soil formation. Over time, bare rock like these are exposed to the elements, with weather like wind and rain, heat and freeze-thawing helping to break up the surface of the bedrock, fracturing it into many smaller pieces. Eventually, these pieces are broken up further and form the physical component of soil. As you might imagine, almost nothing could grow on a pile of fractured rock like this. There are minerals present in the rock, but they're unavailable for the plants. And there's almost nothing to hold water, which is essential for life.
This is where microscopic life comes in. Microbes and algae are able to utilize the minerals held in the rocks and start to grow in the little nooks and crevices. Most importantly, these tiny organisms fix nitrogen and carbon dioxide from the atmosphere, leading to a build-up in organic material. And this process paves the way for another key group of organisms that are instrumental in the process of soil formation. These are the lichens. Lichen gets most of what it needs to survive from the atmosphere, hence its remarkable ability to survive in extreme locations. Lichen is formed from an incredible symbiotic relationship between algae and fungi, and it's these bizarre organisms that would have been the first to take advantage of the organic material left over by the microbes and algae. Not only can lichen survive without soil, but through the secretion of acid, it also chemically erodes the rock that it grows on, which frees up a wealth of beneficial nutrients. When the lichen dies, a small deposit of organic matter is left and gets trapped inside crevices within the rock. As more and more lichen grows and dies, this layer of organic matter, rich in nitrogen and essential minerals, builds up, allowing rooting plants a foothold in an otherwise inhospitable.
You can see there's processes that involve physical as well as biological processes. That's why we have. Thank you. Yeah, you guys are way ahead of the game. But this does not occur on a planet like Venus. So it's basically what is vital to all our life. It supports our plants. It supplies our food and oxygen. Well, it supports what supplies that and absorbs carbon dioxide and nitrogen. Right? It's basically, it consists of humus, disintegrated rock, depending on who you ask. Right? Now you have negative connotations for being soiled or soil, but that doesn't really that's not really where we are in this course. Let's also have just a quick discussion on what's the difference between soil and dirt. Well, dirt is what you find underneath your fingernails. Soil is what you find underneath your feet. So think of soil as the living skin that covers the earth. And it's not just rock, broken up rock particles, which is kind of what I initially was talking about, but it also has living material or organic matter in it as well, or something that was formerly living. See, there's no soil on Mars or Venus. Why? Well, they have plenty of rocks, and to be fair, they do have some erosion on Mars, but it's just basically dust. You don't really have soil. Venus has an acidic atmosphere that cooks rocks into new chemicals. But there's the main component that's missing is life, as one of you mentioned, right? I think one of you said here, it's the life. Yeah. When we look at it from my perspective or my courses, we're looking at it from the soil as an unconsolidated surficial material. And this is what it consists of. Weather, rocks and minerals, organic matter, water, and air. And it has different proportions. These are some interesting notes on it from different books, like, for example, from definitions from this book, Plants and the Environment from 1974. Here's the soil science glossary. I like this one a lot. A soil is a natural body consisting of layers and horizons of mineral and or organic constituents of variable thicknesses, and they differ from the parent material in their morphological, physical, chemical, and mineralogical properties and their biological characteristics. But the upper limit of soil is between the air and the lower limit. That depends on who you ask. I consider soil to be all the material to the top of weathered bedrock. But it depends on who you're talking to. Some people actually consider the soil that's down to 200 centimeters, 2 meters. But no, for me, that's just the shallow soil, 1.5 to 2 meters. The subsurface soil is a lot deeper than that. We've already gone through the different definitions. But that rounds off that part of the discussion. Let us now end our lecture today with a follow-up to our conversation about groundwater. The groundwater basically underlies the Earth's surface almost everywhere, but it's still not always accessible. And sometimes it's not in the shape that it can be drinkable or usable, potable. Sometimes it's kind of difficult to get to, or maybe it's right next to the land surface. What was I saying? Wetlands? I probably should have said marshes. Sometimes it might lie hundreds of feet deep, and it'll be very hard to get to. Sometimes you will find water that just entered the ground after a rainfall event, just an hour ago, 15 minutes ago. Sometimes you might find water at deeper depths that's 100 years old, or you might find water thousands of years. It's been in the subsurface for thousands of years. So coming back to some definitions, an aquifer is groundwater stored in and was slowly through moderately to highly permeable rocks called aquifers. Yeah, Aiden, that is true. Some of the water is millions of years old. So because of the people who came up with the term, I suppose they spoke Latin, so it comes from the term aqua and ferra. It basically means a subsurface layer that can carry water. Some good aquifers are, for example, fractured limestone, gravel, or sand. If you have sand in your soil, you'll have some water flowing through it. You can see how the different aquifers are in the Great Lakes region, the groundwater elevations. 31% of the Canadian population lies in this region. So if you take a look at one region here, I think this is, where is this? Oh, this is Thunder Bay. I'm not exactly sure. I think it is. That you've got, no, let's see. Take a look at the Lake Huron drainage basin. What is a drainage basin? It's basically the entire geographic area that when water falls here and it flows out of the same outlet, one outlet. Here's the Lake Erie drainage basin. So all the surface water and groundwater flows through one outlet. And I think in this case, it's Niagara Falls, near the Love Canal. Here's the Lake Ontario drainage basin. Okay, all right. So that is the end I'd like to do something before I let you guys go today. I'd like to talk about where we're going to go next in the course. We do have a bit of time. We don't have any assessment due right now. You'll have assignment 1 that's due in October, but we need to cover off more material before I issue assignment 1. And that material, so the next week's lecture, we will be working on, we're going to be going into the mass volume density relationship for soil. We're going to be looking more closely at the porosity, specific gravity, what volume means. They're looking at phase diagrams for soil and groundwater, and how we start to look at performing some calculations. Okay, that's where we're headed next week. And let's see where we are in terms of the course outline. So just for the theory portion, I can't really make it. You have to bend your head to the side to read this. So we did our first lecture, Introduction to Soil, Geology, Rock, Weathering. And then in our lecture 2, we got into soil and groundwater, what are aquifers. And we talked about Darcy's Law. Now what we're going to do is we're going to review Darcy's Law again, and then we're going to get into that lecture slide that I showed you guys just now. Okay, so that's where we're going to head to next week. Make sure you stay on top of things with Professor Jovan in the other class. And that is the end of today's lecture. So those of you who want to stick around, you're free to stay and ask me any questions. Otherwise, I'm going to stop the recording now.